So hello everyone to a new EDT community talk. Today we have Jean-Sébastien Sottet. We have three more confirmed speakers. For the 8th of December, we have Edward Camburjan with the topic Bridging Knowledge Graphs and System Models for Self-Adaptive Digital Twins. In January, we'll have Peter Pauls. And on the 9th of February, we'll have Haris Isakovic. So today's talk is about harmonizing the complex, evolving digital twins to bridge data, domains, and decisions. Jean-Sébastien is a lead researcher at Luxembourg Research of Science and Technology. He obtained his PhD from University of Grenoble in 2008, where he pioneered the model-driven engineering for generating human-computer interfaces. He joined LIST in 2011, leading industry and academic collaborations and applying model-driven approaches across governance, compliance, enterprise architecture, and digital twins. His work bridges theory and practice, advancing model engineering to unify disciplines, technologies, and data, from informal models to executable systems. Thank you very much for being willing to present for us today. The floor is yours. I think you're muted.
Yes, thank you very much. So, I hope you can see my presentation. Is it okay?
Yes, it is okay.
Good, good. So, you already presented me. This is collaborative work that I will present from some people working with us at least. As you say, the topic is mainly harmonizing the complex. So I put evolving in parentheses. I will make more explanation of it by the end of a presentation, but mainly it's about bridges, domain data and decision, and making these things harmonized. So first, this is a bit a disclaimer about what we are doing. So we took this definition from Andreas Wortmann about what is a digital twin, which is quite a large definition that encompasses a lot of existing definition and necessarily could fit with the system we are developing. Or whether we have colleagues that still refuse to use the term digital twins because for them it's too much politically connoted, let's say, and they say we are simply building information system, we are dealing with decision support systems, and you will see in some of the digital twins or something we are calling digital twins, they are not really digital twins per se or according to some definition. So we can think we are kind of imposter there. It's also a part of a disclaimer. We start with a naive and optimistic view of how we build digital twins. We have made tool assessment like Azure DT and all that stuff, but we here would like to start from, let's say, a different viewpoint, a more data-driven viewpoint by the start. But we strive to stay pragmatic, so we rely on state-of-the-art technologies, not reinventing the wheel or try to. We would like to involve the stakeholders because they know the job, they know the domains, they know finally how to model things. And we aim to be able to reconsider our approach at any time. So we want something lightweight and let's say quite flexible. So we have three illustrative projects. One is on the from large scale to small scales, from long term to short term. So the first one is the energy transition in Luxembourg. So this is our big national research project. So the scale is the country. Okay, the country is quite small, but it's still a country. We have a long-term projection, about 10 years, and it's covering many heterogeneous disciplines, you will see. In the second phase, we have this hydrogen value chain, still on energy transition, but with a small scale, with one power plant and with 10-month projection, so it's smaller. And we are covering different domains, but let's say it's quite technical. And finally, this is a next generation network system. This is completely technical, only one domain, network digital twins, and the scope can be from one antenna to one country operator, but the response time should be 10 minutes. So I will mainly illustrate the first one because it's showing the needs to, let's say, harmonize things. harmonize models, data, and whatever. We have also different timelines. So the Luxembourg Hydrogen Valley is something that is not existing yet. So it's not really a digital twin per se, since there is no system. So we are in the design phase, kind of proto-digital twin, preparing the digital twin and the system itself. CG Twin is more on the monitoring and prospective things, and the long-term and decision planning is for this energy transition project. We'll stick to these basic principles, so we need to model domains, entities, behaviors, constraints, and rules, and we need to align all these things to put cartography of this, putting on this cartography the existing tools, the functions we develop, the data, and obviously indicator and objectives, because we are mainly dealing with decision support system. Our principle is really to balance this bottom-up and top-down approach from expert knowledge to existing ontology, expert knowledge, whatever they have in mind, actually. But we also need some insight from the reality, from what happens in different data sources like statistics and whatever. And it's an incremental and refined process. And our question is to find an equilibrium between those two things. Indeed, in practice, it can be very cumbersome for the expert to be involved in many, let's say, workshops where we ask them to do ontologies, domain models, whatever. And it should be, yes, lighter in some way, because there are some let's say, reluctance to do that from the experts. So let's focus on this first project, which has been funded by VFNR, which is our national research fund in Luxembourg. And we are managing the large-scale energy transition. So we have to unify the expert viewpoints. The viewpoints actually are on different domains: energy markets, law and regulation policies, very technical with energy infrastructure, let's say not technical with social acceptability, and in between with environmental sustainability, because there are also human aspects. So we have different socio-technical aspects. It's a multifaceted system. And the problem is that everyone sees the other with a specific viewpoint, and actually they see the other more or less as KPI or as constraints, but not seeing their job and the complementarity of each one. In the same time, let's take the example of the energy infrastructure. They say they will drive the marketplace, they will know the regulation, they will model the environmental rules. So they ask the other to follow their leadership to model the system. So it becomes a bit difficult then to have, let's say, a complete view on this system. So in fact, we are not building an operational digital twin. So we'll not deal with the smart meter that gives the electrical consumption of each housing every 15 minutes. We have more longer terms data and also objectives with our project. There are several factors that add complexity to this project. We have a lot of heterogeneous data source with different level of quality, and this is a complex task, but we are not necessarily fully dealing ourselves. We also expect the expert to help us from that. There are existing operational digital twins, for instance, for energy distribution. We have to connect to them. We have not to ignore them. This is held by separated research team, even if they are all located in Luxembourg. They are not necessarily in the same place. They are from different disciplines, and they have partially overlapping domain of expertise. So it can be quite complex. And this system, as I say, is technological, economical, and societal. So it becomes a bit complex. We have also undefined end users, the decision makers. So we try to embed them, but for now, we do not know clearly what are their needs. So our journey within this project starts with participatory meetings. So this is something that is very useful to get to know the stakeholders, so notably the public authorities, the different energy providers, the different stakeholders, and their, let's say, field of expertise. We have some rough understanding on the domain and the stakeholder concerns, what they need to do. We also understand very well the limitations, so mainly due to the current, let's say, regulation issues, and it refines our initial scenarios. But it is not an enabler to build model or consolidating data sources, so building, let's say, a kind of premise of digital twin. So we take a scenario, just to take a subset of this problem. So it's heat pump and district heating. The idea is to favor low emission energies, and heat pump and district heating are the two elements that have been selected. This is an example of how we reuse exhaust gases from enterprises and we produce heat for the different housing. But the idea is really to understand how we could improve the current system. And it calls, obviously, for the different stakeholders and the different domains that, let's say, large discipline that we have identified. And each of them has a different focus, as we see. I will not enumerate all of them, but the change acceptability from user could also depend on the investment. And if they understand the return of investment they can make from changing from gas to heat pump. So it's not so trivial. There is also, there are different kind of incentive that can be proposed, etc., etc. So this is where our modeling journey starts. As it needs to start from somewhere, we need to find collaborative people. And this is not very easy when you say to people, yes, now you have to produce a domain model. And okay, they do not necessarily understand what is a domain model, what is a conceptual model. You can try to find a lot of synonyms like ontology. Some understand, some not. Most of the time they want a nice map. And yeah, and sometimes they don't know what is UML, what is SysML, what are the, let's say, the modeling language that we are usually using in model-based or model-driven system engineering. So we have to dig also the data. So we have kind of data. What is to say around this? I will not take too much time, but we have aggregated statistic mainly. So this is something that then we have to put with distribution on the system, just to have a rough idea about how the system could behave. So sometimes it's playing with statistics and it's not really fun for, let's say, a modeling journey. And we build a conceptual model. And this is really the center of our approach, is really this model. Some call that the ontology, some call that domain model. There are a lot of examples of this in the industry, like the Palantir ontology. It's something also somehow related to those concepts. So let's say that we need a conceptual model. In white, we have put here, so mainly the major part of this diagram, it's coming from existing data. So which information we know we have. So we have a geolocation of a building, we have the address, and this is something that is sure. In green, we have something that are extracted from knowledge. So from knowledge of the users, is derived from data values. So as I say, a distribution, we have a distribution of age of buildings, so we distribute it. But it's not really perfect, let's say. In blue, this is the key indicators, the things that we want to compute on that. And the starting point to go for energy transition is to compute the power demand per building per hour, ideally, depending on the external temperature. And we have to identify missing information. And here, this is approximation functions that we are needed here to compute the insulation level. So we have some idea because there are some information somewhere, but we have to deduce things. So this is where also we may need to enter in more political discussion. So just to have some, let's say, survey on the population about insulation, about renovation, about all that stuff. The second point is this model is really useful for identifying boundary objects, so where they connect to the other domains. For instance, this power demand is certainly connected with other elements. So we compute something that will be used by somewhere else. The heating system, it's potentially something also that is available in the life cycle assessments that they have information about this. It should also reflect the right level of abstraction. So actually, we are still answering ourselves, are we proposing things at the right level of abstraction and the right level of granularity? And we think that the building is the right level of granularity, let's say the housing in general, because we have other scenario like energy community that directly calls to that. So if we can compute things at that level, we can still make aggregation at higher level. But going in lower level is not useful for this project. And the most important is really it's defining a common vocabulary. So each stakeholder will speak the same thing. So when we talk about building, we know what a building is. Obviously, this class has to be somehow extended with other things coming from the other domains, but this is a building, this is a cadastral parcel, this is a locality, so people start to understand themselves and talk about with the same language, so kind of harmonization there. I make a parenthesis on data management. So we have a platform to manage this. Actually, we collect raw data. We have a lot of raw data. Sometimes they are big, sometimes they are small. We structure them. We have some classical algorithm to curate them. And the most important for us is once we have these with domain models together, so the different domains, we are able to provide a transformation that structure the current created data into harmonized data. And this is this harmonized data that will be used by the simulation, by all the tools that we will develop to enable this decision-making process for energy transition. So the modeling journey continue with the functional model. So it's function, it's executable models that are expressed in terms of domain model elements and that are able to provide some insight. And here the idea is to compute the heating power demand based on the decided inner temperature, so 19 degrees, and the external temperature. And so here, this is a code written by our colleague that has to be integrated in this. Some of our colleagues are using dedicated tools for energy system analysis. There are plenty of them, like PIPSA, for instance, that our colleagues are using a lot. And the question is, yes, this should be also integrated as a functional model, but perhaps there as a black box. So we need function specification. So for us, this is very important in the sense that this function specification will allow us to bridge functions together, computation together, but also domain model together. And here this is a simple proposition of what the hourly power demand function could compute. And obviously it's expressed in terms of modeling elements. Each time should be reflecting to the same harmonized definition. But we have some problem on the way because we have lack of data. We have data which are not available. We have data of very poor quality. And sometimes data is even not existing. So there is a lack of digitalization. So this is something that comes out from this project is, yeah, maybe all our institutions are not really ready for a complete digital twin. They already have some digitalization problem in their information system. So this is very important for them, not necessarily for us. This is a showstopper for us. And sometimes the data owner are not willing to share the information for regulation purpose, but also for many different elements. So we are building function from the state of the art, but they are providing very inaccurate results. And some experts are getting very angry because they really want things to, they say, I have this equation, this is something realistic, this is something for the state of the art, and the results you are giving are not very good. We also have in this modeling journey to compute rule and constraints because they are very important. Okay, we all can think about regulation rules, policies, whatever, but there are also the physical limits. This is very important when we put in place in the functional models, AI models that can produce something. Maybe they have not learned the physical limits. And this is kind of let's say limitations to the result that they can give. So it helps us a lot also to understand the quality of the results we are producing. And obviously, we need to trace, to identify the boundaries between the different systems. So we have a system with different concepts. They are linked together, but also functions are linked together. And it's kind of model federation that we are doing here. So associating models together to ensure that at the end, based on the computed power demand per hour, we are able to compute the CO2 footprint and to see if there is an advantage of using that or that technologies and whatever. This is just an example. And we have to orchestrate this function. And this is another model that we have to produce. From a scenario input, we have different elements that are coming together and that are eating together. So we are involving all the different stakeholders because we want to know the heating type market penetration, to know which kind of actually heat pumps are installed, for instance. We have regulation on that. You cannot install heat pump like you want in Luxembourg. Then we have obviously this simulation the power demand according to the type, the CO2 emission, but also there is an impact on the price, and this impact of the price has an impact on the behavior of a citizen. And the way that they use their system will also impact the way it consumes. So we have kind of cycle like there. So it becoming quite difficult, and let's say, to optimize this system because it's a multi-stakeholder problem. And obviously, people are working with tools, not necessarily with a function that they can give you and you can encode that and directly, let's say, link that with your models or your modeling language. You here have to comply with the different source of information like this. And this is the same. So we have a modern data lakehouse at the bottom of our implementation. It's based on, let's say, as you will see, classical implementation for, let's say, big data stuff. This is the state of the art mainly. So we have this at the bottom, I will say, because I'm not a data-driven guy. And at the top, I had this with domain meta models. I call that meta models. Beforehand, I call that models. They are defining a structure, let's say. And they are interweaved with domains, function, and constraints. So these domains, function, and constraints are expressed in terms of the meta model elements. And once we get data from, let's say, the real system, it's created as an input model that is conformed to the domain model. I also add additional information that are not coming from the data, that can come from the expert, or that can come from a process and external things, which also could populate some model elements still conform to with domain. The same way, the domain, function, and constraints are also generating things for us, hopefully. The results, so the thing that we will use for decision making, and it also conforms to the with domain meta model. In between, the results then are stored. Result of the simulation are stored in this modern data lakehouse. So this modern data lakehouse has the advantages to handle different version of things. So this is something that we will rely on. And all models are persisted each time they are created, even by a transformation. So there is a full traceability of this. And I've added squares around models, input, and function, because we need to ensure that all those things communicates together. So it's generating the adapters. We need adapters from the input model, so conversion from this harmonized element into the models. Hopefully, it's already harmonized, so it's already okay. Then it needs certainly some transformation to work with domain, function, and constraint or external tools. And the same way, result model needs somehow some transformation from the result of a function into something that is harmonized also in our repository. So we need to generate those adapters. And the platform implementation, as I said, is able to store different version of the result, different version of the models. And this is something that is of very importance to us, because we want, yes, to store the different simulation. If I see the blue line, okay, it's different simulation. It's kind of Git-like, Git way to represent things. But I can have also branching here for simulation 2.1 and simulation 2.2. It's where I will change some hypothesis, or I will change some model configuration. I will change some computation stuff. I will maybe change the AI model that I have behind the scene because it's, I don't know, more performant or give different insights. So this is, for us, this is the way we see also the importance of the platform. So we also store model configurations. And there is this multi-DT coordination. As I said, this is very important. Actually, we could not have access to this data because this is protected by the GDPR. This is the data owned by also the energy provider. It does not want to communicate where the real lines are, where each people are connected to the network. So what we can do is to ask questions to it. So if we plan to have new heat pump, new electric vehicle reloader in some streets, we can say, is the system able to support it? And the response can be yes, no, and potentially also provide some investment estimation. So this is something that we are preparing with the colleague from Greycat. So based on the Luxembourg KOPR, which is the digital twin for energy distribution in the country. So this is in preparation. I will go faster now for the different other project, because we've seen more or less the approach and the way it works. The difference with Luxembourg Hydrogen Valley is not so different, in the sense that, okay, we are focused on the hydrogen production plant. So this is same model, as I can say. We have energy, we have solar energy, grid energy. We produce something, we store it, and we transfer it to the different use industry. We want to study if it's feasible to have as much as possible green hydrogen produced in our country, based on some assumptions. So the system is not already in place. So we have a simulation, and we will evaluate the value chain. So based on some available data elsewhere, based on behavior functions from the state of the art, or AI models that we take from elsewhere, and obviously compute CapEx and OpEx costs that are necessary for that. And we follow for this project kind of classical model-based engineering approach. So from requirements to full architecture. But in practice, we have already the same problem to elicit expert knowledge, at least at the requirement level. So it is also difficult to have people put into domain models. The same way, the simulations that prepares for a digital twins is something very crucial here. So we try to execute these models. We do not have a problem of different tooling, because we'll have only one. And we try to prepare which sensor we'll need to have, let's say, full DT support at the end. And we need to produce specification, because it will be just specification for the system to be designed. So this is the part that it has been less, let's say, studied now in this project, because it's not yet ready. And if I look to the D2ET project, so energy transition project, we have already, on the contrary, this architecture. So our functional architecture, this is data we collect from the different institutions. So this is our sensors, let's say. And at the same time, we define domain and model function, but we do not have the requirements. So this is where we start from the end. This is the life cycle. I will not spend too much time on that, just to say this is iterative process. We make it grow, and we have some execution phase before it's a concrete digital twin. And then once we have the system, we can just highlight this more deeper and export that to other countries. We are hiring for this project. So we are looking for a postdoctoral researcher on model-based digital twin. So obviously, the idea will be to design the models, to see stakeholders, exchange with them, and obviously to accelerate the decarbonation via hydrogen, hopefully. And you can apply here. So to finish with the examples, here it's the example of the next generation network system. So in the context of the European project CG Twin, we have a similar approach, but with a different infrastructure. So we rely on our colleagues' work in Luxembourg, GreyCat tool, to collect. We do not collect network telemetry, so this is something that is provided by other partners, but they offer the same kind of persistence with obviously less, let's say, big data improvement, but with also very interesting properties like data sharding or things like that. What is important here is the same way they will provide models that are conform to the NDT meta models that we have produced, and will execute function and also store the result model. So this is typically the same, but with a different approach, because in the network, we have already run intelligent controller that are doing adaptation in the edge. So they are already working, adapting the system. They do not rely on a big system, on a network digital twin, just to make adaptation. So it's from millisecond to 1 minute. But for the longer adaptation, or let's say for the broader adaptation, we may have the requirements from network digital twins. And this is where we have harmonized data, functional model, basic model. So we try also to encompass all the things that we have said together, to be sure that things are also working the same way. So here I will not spend too much time explaining this, but this is the way radio intelligent controller is working. So basically the car is moving, it's coming from one radio unit to the other, And the RIC is say, okay, now you're close to this radio unit 2, so you have to move to and to connect to this new radio unit. So it's okay, more or less. With a digital twin, we say, okay, now we have the vector, we know that the car is moving, we can move before, because for, I don't know, signal synchronization with, I don't know, better state, or there are other properties, let's say, that could drive this change. And we can also find if there are potential congestions. So we can also keep, let's say, cars on the first radio unit, because the second one will be completely overcrowded, because a lot of cars will be stuck in the traffic. This is just for example. For the implementation, we still build domain models. In this context of this project, we have produced smart data models also, just to ensure that the telemetry are communicated conforming to this domain model. We wrote this domain model, and we hope to generate it from, this is the GreyCat internal language to build the domain model. And on top of that, we can build views with here synchronization signals. So here it's an antenna with different user equipment connected together, having different signal because they are a different place, and we can compute things based on that. So this is basic, but this is going to be, let's say, regarding the first project I've shown, completely different in terms of reaction, in terms of data quality, in terms of different stuff. So as a conclusion, I will just recap quickly our concerns. So we have concerns for our modeling languages because we struggle doing conceptual modeling. This is really the finding that we have. And the lesson learned is we have difficulties in capturing domain knowledge. We have difficulties in communicating with models. And UML is great when people start understanding it, but it's not necessarily sufficient. So it needs some text, it needs some explanation, and you cannot put a domain expert in front of a UML editor and expecting that the quality of a produced model will be useful. So we have some issue on that. We have also a question of operational model. It means models that could be executable, could be executed. In the case of GreyCat, we have already something that is based on this. In other contexts, we are relying on different technologies just to execute them. Function definition is very important, as I said, because it is the glue between the different functions and between the domain model and the functions. This function definition can be of many forms. This is very important. And the data quality also need to be represented somewhere. We need to be aware of what we obtain. And this data quality could be represented inside the class diagram. And we've made also some work based on, let's say, on annotating this diagram, and also on operating some maintenance task on this class, let's say, versus data, just to ensure that the quality is still good, because it's something that could also evolve through time, and this is an issue. We have also the need to build orchestrating tools and functions. This is very important. So in some case, we can have a simple DSL for derived attribute computation, like for instance, the energy power demand per hours. It's something that could be more or less produced as a DSL for an expert. You can understand the different attributes and make the simple operation we have here. It's just basic mathematical operations. Why not using a general purpose programming language? A lot of our colleagues are, let's say, quite good at producing Python code. So sometimes it's better for them just to provide the code of a function. But we necessarily will have to generate the adapters, because there are external tools, there are machine learning models, there will be black box, gray box functions that we need to ensure that it's consistent with the overall project. So this is a huge task, and this is the different concern that we have and the things that we are still working on in this project. And I will make a last parenthesis, an opener to our research now on, let's say, DT evolution and drifting digital twins. We have three phases here. Before the DT, so it's a preparation. This is the case of Luxembourg project. So we have a big divergence between the models and the data, and hopefully at the end we reach an acceptable state when the DT is running. Sometimes it can drift, it can change a bit, so the way the reality behaves was not really be able to be followed by the simulator engines that we have, for instance, so there is drift there. And obviously the future state and the prediction. And the prediction is, the more you are far in time, the more you are decreasing the quality of the prediction, so the more the models are far from the data. And this is also something that needs to be kept and to be identified before it's diverged too much. So we have to understand why the system is drifting in reality. Is it an exception? Is it a seasonal effect? What happens? We can have a correction factor here. We can refactor the model. We can correct the data. There are different approaches that are in the state of the art and the things we are developing also, at least, until we reach an acceptable delta between the system and the data and the model, so and the system and the model. And for the prediction, for the future state, we have to see where the prediction is diverging from the reality. And sometimes we can have signs of divergence before it happens. And it means also potentially to keep different predictions, or let's say planning of the future states. And sometime here I put two examples. One is because the prediction is diverging, and in the other case, it's because the specification of the system are changing. So yeah, it's necessarily drifting. And I finish on that, and I thank you for your attention.
Thank you very much for your presentation. Yeah, I would like to ask audience if there are any questions.